Okay, in this video, we're going to be looking at the electric field worksheet. And the main one we have to be concerned of is number 1, because this is really the only one that you're going to get like it on the Regents exam. But remember, electric field strength talks about the force per unit of charge, because remember, just like gravity, electricity produces an electric field, and that's what exerts the force. Kind of like what gravity does exerts the force, it's a gravitational field. So we want to try and find, if we want to find the electric field strength, it's how much force is applied over the unit of charge, over the charge. So when I look at here, I've got a charge of 3 millicoulombs, and immediately I go, ooh, crud, I've got an SI prefix there. So I go to the front page of my reference tables, and I find out that 3 times 10 to the negative third coulombs is what I actually need to write. Because we need to be our base unit has got to be in coulombs. And then I keep going down and say, oh, all right, my force, well, that's in 6 kilonewtons. And I'm like, uh-oh, don't want to kill it either. So again, back to the front page of my reference tables, this would be 6 times 10 to the third newtons. And so if I want to find my electric field strength, I'm just going to go E is equal to F over Q. So I take my force, which is that 6 times 10 to the third. That should be a positive third, not a negative third. I apologize about that. Let's change that right over now. So 6 times 10 to the third newtons. I'm going to divide that by my charge of 3 times 10 to the negative third coulombs. And that's going to give me 2 times 10 to the sixth newtons per coulomb, or 2 million, if you want to write it out that way as well. Okay. All right, our next one, this one is a little bit overkill for the Regents level. Now, what you will have to do is you'll have to be able to draw the picture that shows the electric field lines. So what I'm going to do is I'm going to put an actual charge in here. I'm going to put this thing as my charge and say it has a negative 5 coulombs of charge. And then you're going to have to be able to draw that electric field. So the way we do this is we always put a little tiny positive around the charge and say, all right, well, where would that little tiny positive go? Well, that little tiny positive is going to get sucked in. Our electric field lines always show the direction that little tiny positives would end up going. And remember, this is partly due because of the Ben Franklin conspiracy. But you take all those, look at those positives, and I just put a bunch around, and I just draw the lines that show the direction that they would go. And when I draw those lines, that shows the electric field around this charge. And we'll practice on the other one as well. Now, as far as finding out what the size of the electric field is, you'll notice that when I do here, I've got a charge of negative 5 coulombs. So, hey, that's good. But they give me a distance now of 6 millimeters, or 6 times 10 to the negative third meters. At which point I'm like, whoa, 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 that's not in my formula at all. Well, it turns out that there's another one. I told you about it in the Nearpod or in the lesson. But where that comes from is, and I'll go through it really quick, that I know that E is equal to the force per unit of charge. But force, and I'm going to change this to green, we get that from coulombs, which is K, Q1, Q2, all over R squared. And so I'm replacing this F with that, and then I'm going to divide that by my charge. And so what I end up getting, and I'll put this now in blue, when I combine the two together, I get K, Q over R squared. And you're like, well, which Q? Well, because you're only finding out the electric field around that one charge, you only have to use that one charge. So in this case, in order for me to find my electric field, and I'll keep it in blue for right now, my electric field is equal to KQ over R squared, which will be 8.99 times 10 to the 9th Newton Coulomb squared over meters squared. Okay, and you get this from the front page of your reference tables. We got that from Coulomb's law. And then we multiply that by my charge, which would be a negative 5 coulombs. And we don't really have to have the negative, because the negative is going to tell us that it's an attractive. And so what that came from, that we got in our picture over here. So actually, you can just drop off the negative because you're finding out the magnitude and not the direction. And then we'll divide that by the distance between. So 6 times 10 to the negative third meters. We can't forget the square. And so when you get all that, you're going to end up with a relatively big number. It's going to be a 1.2. Let me look at this. 1.25 times 10 to the 15th newtons per coulomb again. Now, if you don't know that, you can just write it all out again and say, oh, okay, well, it's going to be Newton Coulomb squared over meter squared times coulombs. You know what? I did that wrong. I wrote this wrong. I would have lost a point on the Regents because it's Newton meters squared over Coulomb squared. This is what I get for not having my reference table in front of me. So, but the Coulomb's going to kick out, and then we got the meters squared over there. So you're going to end up with newtons per coulomb. Now the next one is almost the exact same thing. And again, I'm not going to ask you anything like this on the quiz or on your mastery check or on the test, and you won't get asked that on the Regents either. It's kind of nice to know for when you make the jump to AP if you go a higher level. But basically, we're going to end up using this equation again twice to find out the electric field strength and then adding them together. But what I want to draw, though, is the picture, because I've got a -10 and then I've got a +2. And I draw them different sizes only because the -10 has more of a charge. It's going to have more electric field lines going to it. And so what I want to do is I'm just going to put a little tiny positive and say, all right, well, where's that little tiny positive going to go? Well, obviously it's going to go away from the 2 and towards the 10, because we know that opposites attract and legs repel. So if a little positive here is going to get pushed away by the 2 and sucked into the 10. If I put one up here, it's going to get pushed away from the 2, come over to the 10, up around like that. And so if I were to put in all these little tiny positives, this is what it would look like. And eventually this one would come around like this can come around like this may go out here like this, and then the 10 is going to have all of these lines sucking back into it. Now, you won't have to do anything like this on the Regents, where they're going to be different amounts, different charges. Instead, they'll always be the same charge or something like that. So you never really have to go that far on it, okay? But real quick, I just want to show you too how we found this, and I'll give you the answer so you can put it through. But when I did the E is equal to KQ over R squared, because the distance between these two, and I'll put this right here again, the distance between these two is 10 centimeters. We want to know what is it, a spot partway or partway in between. So that means that this R is going to be 5 centimeters. Same thing with this R being 5 centimeters. And so we run it through twice. So K, and I'll keep this back in green for our first one. So the 8.99 times 10 to the 9th Newton meters squared over Coulomb squared times my charge, which was -10 coulombs, divided by my 5 centimeters, which is 0.05. But don't forget to square it. And that's going to give you a -3.6 times 10 to the 13th. Newtons per coulomb. And then I'm going to do the same thing. I'll put this one in blue for the other charge, KQ over R squared. And so 8.99 times 10 to the 9th Newton meters squared over Coulomb squared times 2 coulombs all over 0.05 meters. Don't forget to square it. And so that gives us, let me jump down here one more, 7.2 times 10 to the 12th newtons per coulomb. And so what we're going to look at, so initially you're thinking, oh, it's negative, it's negative, it's positive, I'm going to subtract them. But remember, that negative tells you the direction. So in reality, this one right here is pointing towards the 10, so it's going to be going to the left. This one right here is going away from the 2, so this is actually going to the left too. So what I would actually do is I would drop the negative on the 3, and I would just add them together to give me a grand total of 4.32 roughly, 4.32 times 10 to the 13th newtons per coulomb when I add them together. So that's our total. But like I said, you're not going to have to do anything this complicated. The one to focus on is this first one right here. This is one you're going to have to do. And then being able to draw the pictures like over here. So that's it for today. If you have any questions, come on and see me. So everybody have a great day. We'll see you later. Bye.